Hi everyone, welcome to tonight's Bear Research meetup. So I'm Thomas Pan, working eBay in the indexing part. So before we start, do we have anyone want to make any announcement? Anyone? No?
I'm Brian Johnson. I also work here. And I'm hiring. I've been out for 6 months, but I'm back and I'm hiring again.
Right, great.
Dataset?
Yeah.
Hi, I'm Sid. Some of you have seen me. I used to work in another startup, but I've joined a larger organization, LG Labs, and we're hiring, so get in touch.
Thanks. All right. Any more? Any more? All right. So here is our tonight's great speaker, Roberto, and we can see all his information here, and he will talk about one advanced inverted index data structure called Treaps. So without overview, I just hand over the microphone to him.
My microphone. So everyone actually hears me, I know, over there? Yeah? Cool, great. So thank you everyone for coming. As Thomas already explained, my name is Roberto Konow. I'm here as a technical PhD intern. I'm actually from Chile, so like in a couple of weeks I have to fly back there. And this is a work that was published in CIR. I don't know if you have heard about that conference. And it was done with my advisor, that's Gonzalo Navarro, and Charles L.A. Clark from the University of Waterloo, and Alejandro Lopez Ortiz, also from the University of Waterloo. So before I start, even though it's already like 1 hour, or maybe, no, 45 minutes late, but I really want to be really grateful that you are here. It's not every day that a PhD student has the experience to actually present the work to the people that is actually, using and developing and deploying search engines, especially when I'm working about when my work is about indexing, right? So any comments, any questions, that kind of stuff, I would really appreciate it. Maybe that's normal for you, but since I come from Chile, believe me, this is a one life opportunity for me, especially for my PhD. So let's get started. Of course, it's not working. Yeah. Okay. Now, okay. So I will try to make the introduction as painless as possible. We'll try to explain the problem that you probably already know. The related work in terms of how we actually compress inverted lists and inverted indexes, and how we actually process them. I'm going to explain about the inverted Treaps. That's the name that I want for this data structure. It's not actually a name, just naming it like that, right? We'll show some experiments and results, and hopefully the conclusions and future work where we can discuss a little bit about this. So, as an introduction, we'll say we have a collection of D documents, and as you know, these documents are a huge collection of documents. And we can extract all the terms from these documents, and we can create posting lists. So, probably all of you already know this. For terms of this presentation, the posting list will just contain the document ID and some kind of weight, okay? More specifically, the weight will be just the frequency, just for the terms of this presentation, right? We're not adding the position of where that word actually occurs within the document, okay? So this is called the inverted index. Set of terms that contains a list of documents and the corresponding weight that says how important is that term within that document. And we will do this for all the terms in the collection, right? So there are two ways actually how we can construct the inverted index. One is if we sort the list by document ID. So if we sort the list by documents ID, let's say that that's the term meetup, and the posting list will be the document 1, 2, 3, 4, and 5, right? So this scheme is actually really good for an algorithm, a type of algorithm that's called document at a time query processing. It's really good also for processing conjunctive queries or intersections, but it's really bad for processing disjunctive queries or unions, right? It's not that good. On the other hand, we can sort the posting list using weights or frequencies. In this case, for example, we'll have the posting list, in this case, is sorted by frequencies. You can see there that, well, just next to the D5, it's the 10 that represents the frequency. And these are really good for some kind of query processing scheme that is called term at a time. It's usually really good for ranked disjunctive queries, that means for unions. But as you can guess, it's really bad for conjunctive queries. And as you probably know, usually in a real query, we get both, right? We have to process ands, and we have to process ors, and we have to process actually a bunch of other stuff, right? These are just the two basic ones. So it seems that there is no index that I can actually be really efficient to answer both of them, right? You have to just pick one. Usually, what I know is that we sort everything by document ID because the intersections are usually more important than the unions, right? That's what I know. That's not necessarily true. So the problem, well, as you know, we have a huge amount of documents, we have a huge amount of terms. We have to answer different kinds of queries. They have to use hopefully the same space consumption. We cannot have two different indexes sorted by different ways. Has to be really fast, and since today we have a lot of distributed systems, it seems that we can hold the index in main memory. But even though we have a lot of main memory, we have to keep it really small. So another problem is that traditional information retrieval systems, they actually work in a two-stage process. What does that mean is that, well, in the first stage, a collection of D documents, it's processed by the query, and you just extract a subset of that of the results from that query. That will say the top K documents that actually are obtained from that query, and let's say 1,000. Okay, but the thing is that we are going to show to the user only 20, or maybe 50, or maybe 10, right? So after we get, let's say, 1,000 documents, we have to get a different process that is going to be a ranking process, right, for the same query. Okay, and this is usually just 10 documents or 20 documents, or really limited small amount of documents. So the focus of this work is actually for the first stage. We are not touching anything about ranking. We're not touching anything about the second stage. We just want to be, you just want to obtain, let's say, 100 documents or 1,000 documents really fast, and provide that to the ranking process. So just in case it's really late and you're tired and the beer is actually starting to kick in, I will give you a brief summary so you can remember what this talk was about. We're presenting an index that is based on the Treaps data structure. The Treaps is a data structure I'm going to explain. It's not a new one, it's an old one, but it seems that no one actually figured out that it could be used for inverted indexes. The index is actually sorted by document IDs and partially sorted by weight at the same time. That's the cool thing. Allows to filter at the same time as the intersection takes place. So we are doing both stuff at the same time. It's faster, 3 times faster, for ranked conjunctive queries, that means ranked intersections, and ranked disjunctive queries for small k values. One interesting thing as well is that it allows differential encoding for both documents IDs and for frequencies at the same time. Okay? And that the result of that is that we are actually smaller than current solutions. We use 20% less of space. So let's start with the related work. You see this is again the posting list and the inverted index of in this case, the term signs. So this is a document sorted, and you can see there, those are documents IDs, okay? talking here about compression. So the usual way how we compress the index is by creating delta gaps. That means we are just performing how do you say in English? A minus? Okay, so we'll say 4 minus 2 is going to be 2, right? So you see, like, the first document is 2, the second one is 4. We just subtract. That was the word I was looking for. So we're going to subtract the next document ID with the first one, and then we can construct a new posting list that is just going to store the delta gaps. Okay, but we usually need also some random access. In this case, the only way that we can actually get into some place is that we have to start at the beginning, right, and then start summing up until we actually get to the index that we want to, right? So that's why we add some samplings. So we'll keep some of the actual position in the index, and we don't actually going to do anything with them, right? That way, we just go to the closest point that we actually have a sample value, and then we start summing up to the next positions. And we can compress this using gamma, delta, simple 9, rise, before delta, and so on. There are many encoding mechanisms that work. Some of them work really good, some of them work really bad. So this is just a small example. Let's say that that's the original posting list on the top, and the amount of bits that it requires for representing each integer. Okay, so you can see the first one takes 2 integers, the second one takes 3 integers, and so on. If we sum up, we have 18 bits that we need for representing that small list. We just use the delta gap encoding, we can reduce that to 11 bits, right? And this is a chart that was, this is really kind of new encoding mechanism, and here we have a comparison. So on the x-axis, we have the millions of integers decoded by second. Okay, this is how fast it is, the compression mechanism, in this case. And the y-axis is how many bits do we need, right? So the best encoding mechanism should be around here, right? Should be on the right lower corner. I think, and please correct me if I'm wrong, that Lucy uses variable byte. Is that correct? Anyone knows? No? No idea? So you can see variable byte there is one of the slowest ones, and it's one of the biggest ones, right? Variable byte was really cool around, academically speaking, right? Was really cool around 15 years ago. But since 15 years ago, there have been a lot of development in encoding mechanism, and there are some other compression schemes that work really well, right? They are smaller and they are way faster. So, speaking about how we actually process queries now, we just finished the compression part. We're not now speaking about how we actually going to process queries. Disjunctive queries, the best way to actually process them is using an algorithm that is really simple. First, you have to sort the posting list by weight. Then, you have to find some prefixes of the posting list and extract them and accumulate them into an accumulator kind of stuff. Right? The accumulator actually is really tricky, and it's not going to dig into details about that. And we have to, of course, establish some thresholds according to these prefixes. So this is from 1996, Percy et al. Paper from University of Melbourne, if I remember correctly. So this is how it works. Let's say we have 3 posting lists and they're weight sorted, right? So these are also sorted by the ones that have higher frequency. So let's say that we will actually get the first element of the first posting list and we'll add it to an accumulator. And then we can probably add all of them to this accumulator, right? And now we're going to see the next posting list and the next one, and we're just going to add some of them, right? And we, in the accumulator data structure, we will, if there is a match, we'll just accumulate and sum the results, right? If not, that is going to be a new result as well, right? But the accumulator data structure is really tricky to implement, so it's not a straightforward solution. So
how did you construct that threshold? This one
Yeah, that's also a tricky part. Basically, there is a there's a threshold, there's a recall versus yeah, I think it's precision trade-off.
Like equality, like receiving
Yeah.
the curve. Like you have true positives and false positives, and there's two different methods. Like the line, that's equality, and the other method, they use this in other things too. Yeah.
Yeah. So basically, there is a trade-off.
Okay.
If you keep the threshold really low, you're missing some good results,
Mm-hmm.
right? And if you keep the threshold really big, yeah.
The problem is that you have to have labeled data, and it's not doesn't like when your data changes, and the threshold may no longer be
Of course.
valid.
Yeah.
You know, like,
Of course. So there are some more development of this. This is called impact sorted indexes. It's from 2006. It's basically the same idea, but instead of making a threshold really tricky value, they just separate the frequencies in different kind of levels. So they have 8 different kind of impacts. So it's always a trade-off situation. And of course, this is not giving you the exact answer, right? This is not it's an approximate solution. The good thing about this mechanism is that it's really fast. So if you want to get fair enough good results, and if you want to be really fast, this is a good option, right? But this is for unions, right? This is for executing ORs. You cannot, well, you can, but it's really complicated to actually get an intersection here. So what about the ranked conjunctive queries in this case? So they are usually sorted by document IDs, and you just perform an intersection algorithm. There are a bunch of intersection algorithms, right? Most frequent one is that you pick the smallest posting list, you pick the smallest one from there, and you just do a binary search over the rest, over the other posting list, and you keep track of which one was the latest, smallest one of the posting list, and then you move all the cursors to that position. So that way you can skip a lot of documents, and then you can keep going, right? So that's usually the traditional intersection algorithm. There are many more. There are actually one really recent one, around 2009, bits everything. It basically uses bitmaps, so you just do an binary AND on top of posting list, and you can get a lot of results really quickly. That's a really cool one. But after you do the intersection, you basically rank. So you say, okay, this is my intersection results. Now I will add up all the frequencies and that kind of stuff, put them on the heap, on the priority queue, right? And then we'll get the top K results. So it's pretty simple. But there are some more interesting solutions that you can actually rank the documents while they are doing the intersection. Some of them is one, it's called weak AND from Brother et al. 2003. Basically, it has some pivoting scheme to skip documents that are not necessarily going to be at the top K final results. But the most popular one, academically speaking, is the block max. It's from the Think and Sue work from 2011, also published in SIGIR. So basically the idea is to divide the whole posting list in blocks, and you can get the maximum score that lays within each block. So this is more or less the idea. You have a document sorted posting list. These are 3 posting lists, and for each, let's say every 3 elements, you will get the best score, and you will actually store it. So that way you can actually skip, and you just select, okay, I'm just going to visit those 3 blocks, because those 3 blocks are the most interesting ones. And if there is no intersection there, yeah, I don't care about the results. They're too low, right? That's one possibility. They actually achieve really good results, and they are really fast. So this is the kind of the half of the presentation, and this is what I had to learn, before actually doing something. So what my advisor told me was, well, improve the inverted index. As you may know, the inverted index has been developed, studied, tuned, and tweaked for almost 25 years. Actually, I just learned that the inverted index was mentioned in 1967, for the first time, right? And well, yeah, my advisor said, yeah, you have to make it smaller and faster. So of course, no one wanted to try that before, right? So As a student, you can just slightly tweak recent approaches, let's say the block max or that the Pearson stuff and that kind of stuff. You can use, a screwdriver just to get all, or a hammer just to get all the bits out of there. But my advisor actually has some different approach. He's a, academical star. He has tons of paper, tons of collaborators, and he doesn't use either, hammers or screw. The trick. This is the most important part of the talk. So the trick is actually really simple, and I think it was invented in 1987 or something like that. Basically, it follows the two invariants of the invariants from the binary search tree and the priority queue. Okay? So you have two things, keys and priorities. The keys will follow the same invariants as the binary search tree. So the key, that's the label inside the circle, to the left will be lower, to the right will be bigger. I guess I don't have to explain that anymore here, right? But the cool thing is that it also follows the priority queue, or actually the binary heap properties. So for each key, you will have a priority, and basically it sorts itself in order that the most important, or the node with the highest priority will be always at the top. Right? So you can see the keys will be smaller to the left, greater to the right, bigger to the right, and the priorities will be lower as we go down. Okay? So everyone actually follow this idea. Yeah? Cool, because that's why I wanted to call them the inverted trips. So inverted index have posting list or inverted lists. I'm not representing a list, I'm representing a trip. And instead of representing keys and priorities, I'm going to represent documents IDs and frequency. So the most important document will be always at the top. And the documents that are really not that important are going to be really at the bottom part of the tree. Right? And documents with the highest frequency will be always at the root, and we can search for a document in logarithmic time. Now, please take note that this is the complexity. So there's a big O there. Basically, if the distribution is okay, on average, according to the experiments, you get actually almost 2 times the binary search. Okay, so you have a penalty there. It's not perfect because it's not a perfect binary search tree. And as we go down, the frequency will be, of course, lower. So let me explain you the idea, really broad idea. Let's say that we have term 1 on the left and term 2 on the right. We're representing them as Treaps, and we're actually looking for the first one over there. That's a node, that's a document ID. We're looking for that one, and we're going to look for that document on the second trip. We'll start there, and we'll start doing just a binary search or a traversal in a binary search tree. And as soon as we get below some threshold, doesn't want to go below the threshold. Okay, cool. Okay, so we're around here, right? So
no, you're going to fit that one.
yeah. Okay.
Okay.
So we're looking for that node and on the second trip, right? And as soon as we are trying to look for it, there is some threshold T, and if we go below it, well then we just discard everything that is below that node, right? I'm giving a really simple picture here. It's a little bit more complicated. If you read the paper, it's actually like a half-page algorithm, but I will go through a more deep example. Okay, so let's say that the first number in the label of each node is the document ID, and after the comma is the frequency. Okay, so I will start with the first node on the left, and I will create 2 variables, L and U. Okay, just think that there are 2 variables for now. I will start looking for that document ID on the right side trip, and I will keep a lower bound there that is going to give me the sum of the frequency. In this case, it's going to be 8 plus 9, and as far as I know, that's 17. And we'll keep looking at it, and now we'll see, okay, we have a match, right? So two documents are actually the same, and they have a frequency of 14. So that result goes to the result set. And we'll create, in this case, I'm searching for the top 2 documents, and we're going to add that to the top 2 priority queue, or binary heap. Now we'll have the 23 and 4, 22 and 4. We'll have the sum of them will be 8, but there's no match there, so we don't care, and we can get rid of everything that is on the left side. Why? Because there is nothing on the left tree that is actually smaller than that, right? And this means that we can actually get rid of the whole tree that is below it, right? So now we have to search for the 65. Well, the 65 is actually there. So, and the frequency, the sum of the frequencies are going to be 12. So we add that as a result in the top 2 list. So it's going to be there. So 65 and 12. And since we already have the queue, the top 2 queue full, now we can establish an upper bound. The upper bound will be, I will not care for anything that is less than 12, because it's not going to get into the results, right? So that's my upper bound, 12. So now I'm searching for 58. So 58 is 2 plus 3, the frequency, it's 5. I don't care about it. So now I can discard those, and I can actually discard everything that is below it. So that's the actually final result. So if you see what I'm doing here, I am performing the intersection, I am performing the trimming of the intersection at the same time. That's the trick. That's the core idea. For the union case, well, it's practically exactly the same algorithm, but the only thing is that the document ID doesn't need to appear on all the trips, right? So you just have to, if the document ID doesn't appear on all the trips, well, it can still be a part of the solution, right? So what about the size? Great. I have a trip data structure. I have 2 different schemes of sorting, right? Documents IDs and frequency. What should I do now? For representing the tree topology, I need some extra space, and I cannot afford to use extra space. So let's say that we use pointers. So n pointers will take me n log n bits. At the best, that's actually the best case. We can use succinct tree representations. This is something from 2008, academically speaking. Right? There are some representations. It's called balanced parentheses. They use 2n plus O of n bits, where n means the amount of nodes. So we can actually represent a whole tree just using 2 bits per node. That's pretty cool. And we can actually have lowest common ancestor, parent, child, and many other operations in just constant. Just give me one node, another node, I can give you the lowest common ancestor, constant, using this representation. Right? So forget the pointers. This is the coolest way to represent trees. So how is it? This is the balanced parentheses. Let's say that this is an ordinal tree. It's a multi-array tree, actually. These are 3 different ways to represent it. One of them, that's actually what I'm using here, is this BP, balanced parentheses. Basically, you do a pre-order traversal of the tree, and every time you see a node, you will start writing an open parenthesis. Every time you will exit a node, you will write a closed parenthesis. And then you can represent those ones using bits. And you can see there, for each node, you just need 2 bits. You see? Yeah, right. And there are other representations like defoods or louds. Although, and that's going to be the balanced parenthesis of the example tree that I have been explaining, right? And you can represent that using the this bitmap sequence, bit sequence. But the trick is that the bitmap representation has to support rank and select. Rank and select are some really complex operations that was invented by Ian Munro on the 1996. And it basically opens a new area. It's called the compact data structures area in computer science. Basically using that bitmap representation, we can traverse everything inside the bitmap, and the bitmap is actually compressed at the same time. Okay? So, just to make everything more complicated, well, you remember the trip that we have been looking? Well, actually you have to do something extra to it, to get good results. You have to do this isomorphism. According to my advisor, everyone in the world should know what an isomorphism of a tree actually is, but I don't think that is actually the case, so that's why I draw it. So basically, you create a fake node that is going to take as children the most right path of the tree every time. And so the original tree has to be transformed to this one in order to everything to work, to be able to work. Right? That's also a tricky part. And the last part, that is most exciting part. You remember that the tree was able to actually represent documents IDs and frequencies and have a different kind of sorting mechanism? You remember at the beginning that we spoke actually about delta encoding, delta gaps? Now we can do delta gaps of the documents IDs and the frequencies at the same time. So you can imagine that, for example, in that case, those are the frequencies, right? So I can actually get the delta gaps of those. And we can change the numbers, and we can actually get rid of a lot of bits there. And we can also still apply the delta gaps for the documents IDs. In this case, for example, 4 and 9, we can represent the 9 with a 5. The only tricky part is that every time we go to the left, we have to subtract, and every time we go to the right, we have to sum. Right? And for the frequency part, every time we go down, we just have to subtract. Yeah?
How bad is insertion in all of these trees?
Huh?
Insertion. If you have
Insertion?
To add, yeah, insertions. Adding nodes. Are you going to cover that?
What is your guess?
Well, you would love for it to be linear. I mean, something like that.
Yeah, well, it is possible to be linear. It is possible. My implementation, current implementation, it's terrible. But theoretically speaking, we're working linear time insertion. So basically, not constant time, but linear time insertion.
Linear time in document size, not
linear time in document size. Yeah, of course. Only one trick though, they have to be sorted by document ID. If they are sorted by document ID, no problem, it's linear. Right? If they are not sorted by document ID, when you're inserting them, it's going to be logarithmic. Well, n times the logarithm.
in log.
N log, yeah.
Quick question.
Yeah.
How deep do you want that tree to be? I mean,
Actually going to cover that right now, because there was actually a good point. Yeah. So basically, at some point, we actually don't care about the nodes that are here. Probably we're not going to touch them because they are too low. Probably we just want to, don't add the 2 extra bits that it requires to be as a tree representation. So that's why we define a threshold that say everything that is below certain frequency, just represent them as traditional posting lists. Just go back to the most useful stuff, and we represent them using a traditional posting list. And that's a very good trick because actually 70%, at least on the datasets that I run the experiments, 70% of the documents IDs are actually below the threshold of frequency of 3, right? So most of the documents, the term occurs really few times, yeah? We use a kind of a new encoding mechanism. It's called DAGs, direct addressable codes, that allows fast random access to a compressed sequence of integer. That's the best part of it. And we use P4 delta and rise for the F0 list. F0 list means this list where we represent the lowest frequency documents IDs. And we navigate the tree using balanced parentheses. So, experiments and results. We try this with something that's called the Trek Gov2 dataset. Contains 25 million documents, and it's around 560 gigabytes of data. We use the supposed to be the correct queries that should be able to correctly query that index, that has 2 terms to 5 terms. Okay, so the queries contain 2 to 5 terms. And the setup was that big university server with 94 gigs of RAM, and everything was implemented in C++.
Yeah, what kind of documents were there?
They were, that's a crawl of government documents, .gov
Okay.
documents from 2001 and 2002, something like that.
Okay.
Okay, so they are really web kind of documents. They are contain government sites. Okay, so NASA and that kind of stuff.
I see.
We compare our results with the Vulkan Max. That is the one I told you that was really popular. The traditional document sorted inverted index using the traditional intersection, using a frequency sorted index using the Persian algorithm I was speaking about it at the beginning, and the dual sorted solution that is actually based on another data structure. It's called the wavelet tree. That was also a paper with my advisor from 2012. So these are the results in terms of size. The trip is the circle. That's the most important part. And you can see that we are approximately 20% smaller than current solutions, right? And these are for 25 million documents. And you can see, as expected, the growth of the size is linear. Just the constant is going to change. If you see how many, how the size is actually distributed among all the data structures, you remember the F0 list? That's 41% of the whole thing, right? And we need 11% of the whole size just for the topology. So those 2 n bits that we're adding for each node, two bits for each node, is taking 11% of the whole size. And the documents, they're taking 31%, and the frequencies are taking 17%.
Can you just 1 second go back to the previous slide when you have, it looks like Treap without the F0.
Oh yeah.
Is pretty.
It's pretty bad.
Yeah.
It's pretty bad. So without F0 means if we don't trim the lower part of the trip, right? So that's why that part is actually in the presentation, right?
Yeah,
so basically, if we don't take care about the lower part of the trip and we add them to be part of the trip and we use 2 bits to represent them, it's really bad. Right? So the most tricky part is to get rid of those ones and represent them in a different way. It was actually Alejandro Lopez Ortiz, one of the professors' idea. Okay, so you can see here how many bits we're actually using. The trip is the most important one, it's the third one. For the document IDs, we're using around 9 bits. For the frequency, this is really cool, we're using 2.1 bits. And if you compare that to a frequency sorted, so frequency sorted, you will have delta gaps among the frequencies, right? That is going to be really, really small. That's 1.6, so we're not that far. But the problem is that, of course, the trip is going to use more size for the topology. But on the overall, we're using around 12.3 bits for the documents IDs and for the frequencies. And that's better than all the other options. So this means roughly 1.7 bytes around. Yeah, 1.6 bytes. Okay, let's see the intersections. So the trip, again, is the circle one. This is the most depressing part of the whole presentation, right? This is the top K. If you see, it's really fast for small k values. So if we want just, let's say, 30 documents, it's really fast. It's completely beating everyone else. But if we want more than 30 documents, the other mechanisms are better. This is going to be improved. New results, new implementations, new tweaking, more hammer, more screwdriver is getting me to 100. I'm hoping that with new techniques I'm getting 1,000. Okay, it's hard. In terms of the query length, this is the intersection for k equals 10. For 2 terms, we are intersecting 2 trips, really fast. 3 trips, okay. 4 trips, fine. 5 trips, no. We are not good for many trips. So we cannot intersect many terms. In the case of union, this is for k values. Okay, in the case of doing an OR, we're pretty good up to 130. Okay, let me remind you that the parsing one is an approximate result, so it's not actually really comparable, right? It's just like for a point of reference. And in the case of the amount of Treaps that we actually doing the union, well, we have the similar results as intersection. So we're good up to 4 Treaps. Okay? And this is also a very interesting chart. This is how many documents we touch. We actually have to compare to get the intersection. So that straight line over there is the plane intersection. Okay, so that's the baseline. If you do a plane intersection, you have to touch, in that case, around 22,000 documents. Okay. If you use the Treap, you will see that for different k values, up to 1,000 approximately, you're actually touching less documents that perform in an intersection. So this means that theoretically speaking, I'm able to get up to 1,000 documents faster than doing a simple intersection. And here you can see how many actual F0 documents I'm touching while I'm doing the intersection. So, as conclusions, well, the idea is to use a new representation using Treaps for the inverted index. We present a smaller index that is able to differentially encode both documents IDs and frequencies. It's faster for those cases. I should change the title of the topic to be like faster and smaller inverted index in some cases, or for some queries. It's better for shorter queries. And yeah, so I just add this for if you are interested in bleeding edge, state of the art in terms of academics stuff. There is a new paper for 2013. It's called Exploring the Magic of WAND. Basically, it's a new query processing scheme. It's really interesting. Optimizing top K documents retrieval strategies for block max indexes. It's basically a follow-up of the previous work of block max. They're actually improving their results. If you like to test new compression schemes, this one from 2014 is really, really good paper. It speaks about how to actually implement fast and efficient compression and decompression schemes. And score-safe term dependency processing with hybrid indexes. These hybrid indexes, that was a really cool idea. They represent some of the posting list as posting list and the other parts as bitmaps. So for some parts where the documents are really dense, they can use this parallel SIMD, SIMD operations from the processor and just grab the intersection of those 64 bits in just one operation, right? When the documents are really dense, right? And when the documents are really sparse, they just go back to the posting list, right? And this is going to be really hard to beat. It's really fast. And yeah, that's pretty much it. This paper was again presented in CIR 2013, and those are all the emails from all the people that was part of this work. Yeah.
Thanks, Roberto. Thanks very much. So, do we have a question?
You took this government database, but there are all sorts of other things you could have tried on, and since you're a temporary employee of eBay, did you get a shot at using their database? I have no idea how big that is.
I'm actually working on it. Working on it in terms of asking Thomas and my manager and other people to get hopefully the data, because
something like all descriptions of all all things
of course,
for sale.
Of course. But I have to get the authorization, law, and the NDAs and that kind of stuff to test the data with these techniques, because I'm not able to do it while I'm here, so I probably need to take the data with me and test it, back home. But I definitely want to do that. I mean, it's totally different. The thing is that if someone really has a lot of data and wants me to test this solution with it, I would really, really like that. Because for students and academics, it's really hard to get real data. It's really hard. And the only data sets there are like 2 data sets. Even queries, there was a guy that was fired because of sharing the queries. This AO, American Online search engine. There was some research scientist published the query logs, make a huge contribution to the academical world, and there was some journalist that was actually able to track one person using the queries. So he looked at the queries and was able to go to some place and say, hey, you lady, you did these queries? And the lady said yes, and that was the end of the story. So then after that incident or accident, no one actually wants to share anything to the academic world. So let's hope eBay is going to provide us. What do you think?
Yeah, someone said yes. I have no objection.
I think no.
No?
There are other document collections, the ACM or IEEE, potentially can let you into their indexes.
Yeah, haven't thought about it. But the other thing is that you have to synchronize with the other guys that are working on the same thing, right? So if you want to compare your index with the other implementations, you have to use exactly the same data as the
What
other
about the
ones.
Reuters?
Huh?
The Reuters index. They have a big set, and then I can think of like 2 or 3. Maybe I can talk to you afterwards. But.
That will be awesome. That will be awesome.
Roberto, quickly, what was your average query term size?
2.7, if I remember correctly.
Okay.
Yeah, I know. So one suggestion that one actually made, I didn't do it, is that I should add this whiskers kind of chart. This, with all the different percentage of the distribution for each value, right? Because maybe it's kind of biased if you just show it like that.
We could expect query for similar documents to be doing pretty poorly here, given that as K grows, things get worse.
For
similar documents. Find me documents that are like this document.
You're thinking like topic maps or something?
Yeah.
To be able to, yeah. That's kind of like categorizing or your documents based on certain word frequency. Can you use that to?
That's actually really interesting.
Topic.
Yeah.
I think that's
what NSA does.
How do you
Can't
know?
make contacts here if it works.
How do you know?
I heard somewhere.
So yeah, that's actually really interesting. Maybe we can do something with the topology of the tree and do some kind of classification that kind of sense. But I think it also has. We just published a new paper that uses this for matrices. So imagine a matrix like an OLAP, dimension, 2 dimensions or maybe 3 dimensions of the OLAP view, right? And you can apply exactly the same thing as the Treaps and also the delta encoding for performing range queries over a 3-dimensional cube. Well, of course, it's a cube, it's 3-dimensional, over a cube, right? And we got really good results as well. So we're finding new applications of this, and I have to find it because if not, I'm not going to graduate. So any suggestions, please?
There was the Netflix challenge, which this seems like it might fit in there, except documents are probably very small. But,
yeah. So documents will be.
And they do provide that data.
Yeah. Also the movie lens. Actually, never tried that. I don't know if this makes some sense for recommender systems to actually intersect things with thresholding in terms of get the best. Like if I have two users, right? I want to get the best items that those two actually rated together, I don't know if that makes sense for a recommender system. Maybe for some kind of collaborative
Well,
filtering.
it's a different,
Yeah.
different dimension. I
Yeah,
mean,
yeah, yeah, yeah.
It's
Yeah.
a different way of thinking about the problem.
Yeah.
But this is where indexes are very important.
Yeah, actually-
There was a lot of money to be made if somebody
Yeah.
was
Yeah.
really clever about their indexes.
Actually, I was really shocked, but for recommender systems, for representing the user rating matrix, the first guy that actually implemented an inverted index and evaluated was in 2012. I was like, of course, you have to represent them on an inverted index, but the first guy was in 2012. So it seems that everyone else was using a matrix representation. I don't know.
It's getting bigger than new cluster.
Yeah. So, do you have any other suggestions, or do you think this is actually deployable in some kind of scenario?
It all has to fit in memory, though.
That's not really that big of a problem.
Well,
Yeah.
it depends on which kind of data you're working with.
Okay. I think the biggest thing is you need different document types. You can't just run it against one data. I mean, you can, but I mean, if you want to, if you want to find problems, if you want to see if things hold, then you need to try to index different types of documents.
Yeah.
That's when all of a sudden you're going to realize, like, oh, that was really great for.
Yeah. We're actually wondering if we can add some, also some kind of parallel execution of it. So we start at different points of the tree, and we try to find in parallel using several threads, different
Sharded
intersections.
data, so-
Yeah.
What if you don't want the top pay documents, but you want to walk through all the documents? You want to do, we do that at eBay, we want to do counts.
Yeah.
When you do the query, you get the exact count of documents, but kind of more importantly, when there's that category hierarchy in the left nav, you get, there's 57,000 dresses,
So the
27,000
histograms,
shoes.
right?
Right.
Yeah.
Yeah, so you end up traversing through all the documents in order to count them.
Yeah. So
How
that's
much of a difference does that make?
it's basically doing a traditional intersection or traditional.
F0, your pruning doesn't work
Yeah,
anymore.
the pruning doesn't work there. Yeah. So maybe according to some tree properties, you can guess the final result set size. But what I heard is that the users at eBay really complain when the histogram information doesn't match the actual query.
Yeah, people are really excited about making sure those counts match.
Yeah, it's like 4 million items, and if they don't count 4 million items, it's
You couldn't say approximately.
yeah, it's much more easier. But yeah, no, in that case, there is no trimming that is. So
Google does this all the time. They give you a count of documents, and then you go down to the third page and they say, "Oh, we're trimming off everything from here," because they're all alike.
also does that for Gmail, I think, when you search for a conversation.
Roberto, can you talk a little bit about finding the gist of inverted tree? I mean, what was it like, investigating it and making sure that it worked, and then this is the data structure that I need. I mean, can you talk a little bit about that?
Oh,
How many other bad data structures did you
Yeah, exactly.
sample
Thank you.
first
Thank you,
before
Brian. Yeah.
What did you throw away?
Because that's like the holy grail in this whole thing, right? Is really discovering that. I mean, other stuff is important, but
so basically, if you read the paper, there is one sentence that is actually where all the motivation came from. I didn't mention here, but there is some, at the beginning I show you this block max stuff, right? So basically all the motivation was from here. This was, and I think is now, again, the fastest and the most efficient way to do intersection and ranking at the same time, right? So basically the idea was to just skip all the blocks that you don't care, and just visit the blocks that you might care, right? And this was with a fixed size. So you split all the posting lists into fixed size blocks, right, with containing a fixed size of elements. The trip idea is doing exactly the same, but it's not fixed. It's a new kind of it's a organization. It's a, how do you say it? It's a kind of organization that is actually sorted by that kind of sense, right? So I was trying to use something like this with a priority queue. So let's put the blocks into priority queues first, right? And then how do we actually do the search? And I came up with the idea for using Treaps. I actually didn't know that there was a data structure named Treap, right? Just say, hey, I can just mix a binary search, because I wanted to do a binary search inside a priority queue. So I built a binary search plus a binary search tree plus a priority queue, and it got really good results in terms of speed, right? Just like a really small prototype. But the space was terrible. As you pointed out, if you just represent everything, the space was terrible, because you needed to, at the beginning, you need to actually represent all the pointers. And that's just not affordable. So then, since I'm working on compact data structures, I applied everything that I could, and I had to pick the best ones, and then I just get rid of many of them because they were not cache friendly. So I was jumping all over away from the memory.
So you were like experimenting and putting everything, okay.
So that's basically, I got like a rough idea, and then I just grabbed my hammer and my screwdriver and start tweaking that idea until I got really, fair results. Right? And of course, there was the conference deadline. So, so we wanted to finish before the conference. So I have a bunch of more improvements actually that are already implemented and already tested. So that's why I can tell you that we are now able to make it even smaller, even faster. But still, we have some conditions. And we're not. Of course, the first implementation is not dynamic at all. The new one is going to be dynamic, so you can add new documents.
So this presentation is available? You get to Brian to put on that?
I think
Yeah,
so.
it'll be up on the meetup.
Awesome.
Yeah, I think so. The only thing I guess is I have to take out this picture.
No, it's not every day that you hear a paper or a topic and that somebody says, I am using a new data structure. I came across this thing that solves my problem.
Yeah, it was.
It's pretty neat.
Yeah,
I think.
very nice.
Yeah. So in my case, it's my way out of the PhD.
I actually learned Treaps back in college, and I forgot it never came up. It's nice to see it used.
Yeah. I never heard about it actually. I didn't learn from college, and actually I was telling the idea to one friend, and my friend said, "Hey, you're using Treaps." I say, "Wait, there is a data structure that is actually doing what I'm doing?" Because yeah, it's like really old. And I was really disappointed. It's like, oh my god, I was so excited with the cool new data structure I invented, but no.
It wasn't even our textbook. The professor just introduced it to a lecture.
And the current usage of them is like for randomized search. So it's totally different usage. I mean, they use it for a special case when you have to search. I don't remember actually, but when you have to search with a certain conditions, they're really good. But usually they're not used.
I've forgotten what they were until I saw you talking.
Yeah.
Cool. Thank you.
Very nice.
So yours?
Yeah, here.
Okay, cool. Okay, so thank you very much for being here and for all the comments. If you can provide me with some data, that will be awesome. If you can provide me with more thoughts and new ideas, that will be awesome as well. And yeah, thanks.
Thank you, Roberto, and thanks everyone. So we're done for tonight.